Hello, and thanks for your continued interest in the subject of shaft alignment. This tutorial covers the phenomena of bracket sag and discusses the reasons why it might be a good idea to disengage couplings when taking alignment readings. Hopefully, this will assist anyone who is responsible for installing or maintaining rotating machinery such as motors, turbines, pumps, fans, gears, compressors, and generators, for people who evaluate the operational or mechanical performance of machinery, and for technicians and engineers who are responsible for rotating equipment. So, this information is intended for trades personnel, maintenance supervisors, training instructors, mechanical procedure writers, vibration analysts, engineers, maintenance managers, and any interested operations personnel. Using mechanical brackets, gravity has an effect on the tooling, and the bracket sag that exists in your setup must be measured and compensated for. We will also discuss whether or not it is a good idea to keep your couplings engaged when taking alignment readings. If you use mechanical brackets when aligning rotating machinery, you must measure and compensate for bracket sag. When a bracket and span bar with an indicator out on the end of the span bar is used on horizontally mounted shafts, gravity will act on this cantilevered beam. When the bracket is up and the span bar is in the top position, gravity is bending it downward toward the pipe on top. This is similar to what happens when you walk out to the end of a diving board at a swim pool. When you get out to the end of the diving board, your weight elastically bends the diving board. Depending on your mass, the diving board may bend a little bit or it may bend a lot. However, when we flip the bracket and span bar and indicator upside down, gravity, which is still working in a downward direction, is now bending the span bar away from the pipe on the bottom. The bracket sag is the total effect of how much the span bar bends toward the pipe on top and then away from the pipe on the bottom. There are 4 factors that affect bracket sag: the amount of overhung weight, the weight of the dial indicator, the weight of the clamp that holds the indicator to the span bar, and the incremental weight of the span bar itself. The next factor is the span of the bracket. Are you reaching out 4 inches or 12 inches or 20 inches? The next factor is the stiffness of the span bar and bracket. And the last factor is clamping force or clamping pressure. Usually, after I capture the alignment readings, I remove my brackets from the shafts and be careful not to disturb how they were set up to take measurements on the shafts of the drive system I was aligning. I use the same indicator, I don't change the span distance, and I find a fairly rigid piece of metal pipe about the same diameter that the shafts were clamped to. I position the bracket and indicator so it is touching the top of the pipe, or in this case, another bracket I used as the contact point for the indicator. I plunge the stem of the indicator in about halfway, zero the indicator, and then flip the entire arrangement upside down and note the reading on the indicator. It is usually a negative number. This is the amount of sag there is in this bracket for these sets of readings on this particular drive system. A lot of people know about bracket sag. What many of them don't seem to know is this. If you are, for instance, taking a set of reverse indicator readings on a motor and pump drive system, and you had 12 mils of bracket sag, Here are the readings you must obtain to ensure that the motor and pump shafts are aligned with each other. If you are spinning zeros, your shafts are misaligned. Not until you get -12 for both bottom readings and -6 on all the side readings will you know that the motor shaft and pump shaft are in line with each other, just like the pipe you check the sag with is in line with itself. Any field readings you get must be compensated for bracket sag before you can determine what moves are needed to correct a misalignment condition. Let's say we are going to take a set of reverse indicator readings between a motor and a pump. These are readings that we are going to get to measure in the field knowing full well that there is sag in our bracket. But for now, our efforts should be concentrated on getting good measurements. We'll deal with the sag in a minute. Earlier in this tutorial, we showed the reverse indicator method, which can be performed with just one bracket and one indicator. Perhaps we start off by clamping the bracket on the pump shaft and place the indicator on the motor shaft. We plunge the stem of the indicator in at top, zero the indicator there, and sweep around the motor shaft. On the west side, we get a -54. On the bottom, we get a -72. And on the east side, we get a -18. We take the bracket off the pump shaft and clamp it to the motor shaft and place the indicator on top of the pump shaft, plunge it in, zero the indicator, and take a set of readings. On the west side, we get a -46. On the bottom, we get a +32. And on the east side, we get a +78. We then take the bracket off, find a pipe, clamp the bracket to the pipe, set the indicator on top of the pipe, rotate the assembly upside down, and notice that we have 12 mils of sag from top to bottom, and we also notice that we have a -6 on both sides of the pipe. Understand, we cannot use the field readings to figure out how to align our shafts. We are going to have to compensate the field readings for the sag in the bracket. What we're going to have to figure out is, what would we have really got with a perfect bracket that had no sag in it? So let's take this one measurement at a time. Starting with the bottom reading on the motor, we got a -72 there. So when we zeroed the indicator on top of the motor shaft and swept down to the bottom of the motor shaft, the stem of the indicator moved outward or upward 72 mils. But as we swept to the bottom, the bracket sagged away 12 mils. 12 mils of that -72 is due to the sag in the bracket. So to get the sag out of there, we take the amount of the sag, 12 mils, and add it to the bottom motor reading. -72 plus 12 equals a -60. So, with a perfect bracket that had no sag in it, we would have got a -60 on the bottom of the motor. Now, let's take a look at the reading we got on the bottom of the pump. There, we got a +32. Now, this means that when the bracket was clamped to the motor shaft and we zeroed the indicator on top of the pump shaft and swept to the bottom, the +32 means that the stem of the indicator got pushed in 32 mils. But in the process of sweeping to the bottom, the bracket sagged away 12 mils. To compensate for the sag, just like we did for the bottom motor reading, we add 12 mils to the bottom pump reading to get rid of the sag. So, plus 32 plus 12 equals plus 44. With a perfect bracket that had no sag in it, we would have got a plus 44 on the bottom of the pump. What would we have got for the side readings with a perfect bracket that had no sag in it? Well, we have to add 6 mils to each of the side readings. For the east motor reading, minus 18 plus 6 equals minus 12. For the west motor reading, minus 54 plus 6 equals minus 48. For the east pump reading, plus 78 plus 6 equals plus 84. For the west pump reading, minus 46 plus 6 equals minus 40. These are the readings we must use to figure out how to align our shafts. If we try to use the field readings, we're going to come up with wrong answers for any vertical moves. There's one more thing we should talk about before we complete this block of information. In the tutorial on vibration, we discussed the phenomena of elastic bending in shafts. We talked about the natural elastic bending of a shaft supported at both ends with bearings, and the fact that the weight of the rotor in between these support points will produce a catenary curve in a shaft. We also talked about the fact that moderate to severe misalignment will elastically bend the shafts into an S-shaped curve. Since the main topic of these tutorials is to learn how to align our rotating machinery, it is assumed that you realize that you are probably going to start off with shafts that are not aligned correctly, and that you also know that there is a coupling connecting the two shafts together. You also know that we are going to be taking measurements across the coupling with brackets and indicators or some other type of alignment measurement system, which means that we are going to be clamping brackets and placing measurement devices somewhere in the areas circled on the illustration. Notice that the ends of each shaft are elastically bending to accommodate the misalignment condition. If we were to release the coupling, the shafts would spring back to where their center lines of rotation are at, which is where the bearings really want them to be. However, if we keep the coupling engaged and attempt to take measurements on shafts that are undergoing bending stresses, the readings we get will not be representative of the true center lines of rotation. This is probably the number one reason why people who align rotating machinery have to make several vertical and lateral moves to achieve acceptable misalignment tolerances. Therefore, if you want to measure the true center lines of rotation, it is strongly recommended that you disengage the coupling and release any bending stresses in the shafts. If you have an alignment measurement system that requires that you keep the coupling engaged, you might want to look for a better system unless, of course, you enjoy making several unnecessary moves. To illustrate what I mean, here I'm taking a set of reverse indicator readings across an engaged flexible coupling which has a moderate misalignment condition. I took a set of readings with the coupling engaged, then I unbolted the coupling and took another set of measurements. Here is an alignment model showing the side view of the motor and pump shafts along with the reverse indicator readings when the coupling was bolted together. Each major division in the up and down direction on the grid is 20 mils. If I would have used these measurements, it would have required me to remove 90 mils of shims under both outboard feet and 30 mils of shims under both inboard feet of the motor. Thank goodness I didn't do that. Here is the alignment model showing the side view of the motor and pump shafts and the corresponding reverse indicator readings after the bolts were taken out of the coupling and the spool piece connecting the two shafts together removed. This is really where the shafts are at. Only 6 mils of shims needed to be removed from the outboard feet and 8 mils of shims added to the inboard feet of the motor. Here's a comparison before and after the coupling was disengaged. That's quite a difference in perceived and actual shaft position. With an 8-inch separation between the flexing points in the coupling and a 17 mil maximum deviation at the flex point on the pump, there was only 2.1 mils per inch of misalignment in this drive system. It doesn't take much misalignment to elastically bend shafts. Gravity is a nice thing, but it can affect devices we use to take precise measurements. If you use mechanical brackets, you must measure and compensate for bracket sag on horizontally mounted shafts. If you're working on vertically oriented shafts, bracket sag is not an issue. There's a little math involved in making validity rule checks and compensating field readings for the sag that you have in your bracket, but it is well worth your time to get this embedded in your thought process. I frequently get strange looks when I'm explaining about elastic bending in shafts. It's natural to be suspicious about this because it is difficult to visually see the bending occurring with your own eyes. If you're in doubt, then try this experiment. Pick a drive system and align it. With the coupling on the shafts and engaged, install 100 mils of shim stock under every foot on one of the machines. Set up your alignment measurement system, take a set of readings across the engaged coupling, and solve for the moves in the machine you put the 100 mils of shim stock under. Let me know if the solution was to take out 100 mils from every foot. Again, thanks for your interest in this subject material. I hope this final tutorial in the introduction to shaft alignment has been helpful and that this information assists you in performing your work a little easier and with more accuracy and less frustration. I also hope this has piqued your interest to continue on with not only the basic tutorial series, but also the intermediate and advanced tutorials.